Hey everyone, welcome to Chapter 5 and Assignment 58. Here we're going to be talking about EVT, which is the extreme value theorem. It, like many of our other theorems, has a precondition. The precondition is um, if f is continuous on a to b, then so remember, as always, College Board wants us to address these somewhere, often, sometimes. Um, but before we get to what comes after the word then, all right, I'm sorry, we'll do it. Then F has both a max and a min on A to B. So think about that statement for a minute. If you got a function and it's continuous on from this x value to this x value, then what we know is that that function is going to have a minimum and a maximum somewhere on that interval. It could be between the 2 points, it could be at the end points. We don't know. Now, anyone have a problem with that? Any situations where that doesn't seem to be the case? Let's think. Here's a line from A to B. It's continuous. This line is continuous, and yes, there's a minimum for this f at A and a maximum on this f at B. Even if we have something like this function, and we make our A and our B here, we see a minimum and a maximum. Isn't that interesting? It kind of looks like the minimum has the same y value as the maximum. And that's going to turn out to be an awkward uncomfortableness in this section, which, don't worry, we'll quickly forget about and move on to being able to figure out maxes and mins using our calculus in a more comfortable way than what's proposed here. EVT is an existence theorem. It tells us that there's a minimum and a maximum, doesn't tell us how to find them. Hey, speaking about minimums and maximums, is y equals 7 a function? Okay, let me give you a domain. Is y equals 7 a function on this interval? Well, not only is y equals 7 a function, but y equals 7 is continuous on that interval. So what was it that EV said again? EVT said that from -4 to 4, or on A to B, any continuous function would have a max and a min. I'm sorry, can you point out the maxes here and the min here? I can't seem to find them. Oh, what's that? Did you hear a lame alert? Blearing? Yes, I did too. When asked about this situation, what does EVT say? EVT says, oh, well, yes, it's clear and it's obvious. There are an infinite number of minimums and maximums. I don't find that very, very nice. And I'll say that while we're starting to look at EVT as a way of determining mins and maxes, um, we're not going to use a lot of what is presented here as our technique. So, yeah, because all we know is that a maximum exists. And what we can think about is theorem 2 here in this section says local extremes. Well, if f has a local or relative min or max at x equals c on A to B, and, wait, there's more, and f prime exists at x equals c, then f prime of c is going to have to be 0. Huh? What are they getting at here? Okay, so they're getting at a thing that looks like this. If I have a function, and that function, a to b, and that function has a local min or max at x equals c, then, and, wait, so 1, there exists a max or min. 2, f prime of c exists also. In that situation, we know that f prime of c is going to be equal to 0. Yeah. So that's nice. A couple of things that this sort of, well, here are my questions. Okay, with that in mind, we're talking about A to B. Here's A. Let's call this B. Let's call this C. Let's call this D. So my function f is continuous on A to D. Great. So EVT says you gotta have at least one min and at least one max. Sure. I got a min and a max. I'm all good with that. But then we go on to say, if f is continuous on A to D, I'm sorry, if f has a max or a min at x equals c, or in this case b, on A to D, then f prime of c equals 0. Well, I agree with that. But I'm a little troubled by these, because I can't have, can I have a, I guess I can have a 0 slope and an endpoint. Huh. Okay, I can go, but ooh, a one-sided derivative at that point. You know, I feel like EVT is leaving out, or I'm sorry, theorem 2 is leaving out endpoints. I also am troubled by the fact that I can have mins and maxes at other places besides endpoints, or where f prime is equal to 0. Let's take our dear old friend absolute value of x. Hey, what you got there? That's a min. Okay, I got a min at 0, 0. Is f prime equal to 0 here? No. And that's why theorem 2 has to put in that little thing about if f prime exists. Okay, so really what I'm saying is I don't have a lot of use for for theorem 2. I don't think it's worth the time and effort. I don't think you should struggle with it. I do, though, take an understanding from these sections, or from these things that are talked about here in 5.1, that mins and maxes occur 3 places. 1, at endpoints. 2, where f prime equals 0, and 3 where f prime is undefined. Now, just because f prime is 0 or f prime is undefined doesn't guarantee a min or a max. It merely suggests a min or a max might exist there. All right? So what do I mean by that? Well, look, let's take y equals x to the third. Okay? Here's y equals x to the third. And what's the derivative of this function? Y prime is 3x squared. Okay, this derivative is equal to 0 at 0. So on this y graph, I see that slope of 0 there, but is that a min or a max? No. So just because you have f prime equal to 0 does not guarantee that you've got a min or a max there. Likewise, if f prime is undefined at a point, do you have a min or a max? Well, look at these cases. F prime is undefined at x equals c. So, yeah, no derivative possible there. Likewise, if I had something like a hole in the graph, if f isn't continuous, then f prime doesn't exist. Do I have a min or a max there just because f prime is undefined? No. So what we're getting here is a list of where mins and maxes can occur. The other thing I want to bring up here is, and don't get me wrong, these are going to be hugely important just for knowing where mins and maxes can occur, right? But it won't be until the next section or the section after that that you start to say, oh, that's what he was on about, okay? I do want to say that not all mins and maxes are created equal, and we talked about this last year in pre-calc. Mins and maxes come in two flavors. There's relative, sometimes known as local, and there's absolute or global. AP tends to use these words. And here's my situation. Look, we've got Mount Lemon here. Mount Lemon, it's the tallest mountain we got. It's our local max. Is it, though, the global max? Is it the absolute maximum of a mountain height on the planet? No, there's lots of others. So there can be lots of relative or local mins and maxes, but unless they all have the same height, there's only one global or absolute min or max. It is possible to say something lame like you have an infinite number of relative and local mins and maxes here, but you also have an infinite number of absolute and global ones. And really, you shouldn't hang out with people who say things like that, because that's just silly. But I do want to say that we are going to be concerned with mins and maxes. I agree. I'm getting these mins and maxes where f prime is equal to 0. I see minimums occurring at endpoints here. So I'm okay with the idea that mins and maxes can occur at endpoints when f prime is equal to 0, or even if I turn this into a piecewise function instead of a polynomial. Look, the limit of the slopes from this side might be approaching 0, but the limit of the slopes on this side is not approaching 0, and so the derivative would not exist at that point, and yes, there's a max there. Okay. We're good? Do we have everything? Oh, relative min, relative min, relative min, absolute min. This absolute min is also a relative or local min. When we talk about local, I kind of really like that word because it's talking about in its neighborhood. In its neighborhood, it is the biggest or the smallest. Mount Lemon in our neighborhood is the biggest. But On the planet, not so much. Okay. Um, Absolute max, no, that's just a relative or local max, and over here we have a relative or local max, and we know that this one is the absolute max. So I will say that what we will be concerned about is not only finding where mins and maxes are, but we're also going to be asked, because this is EVT, the extreme value theorem, we're also going to be sort of trying to figure out which of these are absolute maxes and which of these are absolute mins. And what we're going to be told to do in this section is to evaluate the function at each of those points and just compare y values. At least that's going to be true this semester. We'll have another method next semester that will be that will involve the candidates test and will be maybe a little happier. I mean, my concern here is that just because I know the y value at a place doesn't necessarily mean that I know whether I have a min or a max at that place. So, for example, if I put E over here and I make this the same y value as this, well, this minimum y value and this maximum y value are going to be the same y value. So how can I know whether one of them is a local min or a local max? So I'm not really fond of this approach, but when we do the candidates test next semester, it is going to be the case where we're going to come back here and plug all our candidates into the original function to help us figure out the answer to these. But for right now, let's just play along, and having now brought up all these things that you weren't concerned about in the first place, that you might be getting concerned about now, yes, don't worry. Let's just go, talk a little more, and then we'll do some problems, and you'll say, oh, why did we go on all that? It was just this simple. Yeah. Okay. Next, there's going to be some language. There's critical point. A critical point is an interior point on A to B. And what we mean by here interior is that that point is not an endpoint. Okay, critical point is not an endpoint. So it can't be A or B, but any point in between A and B, where f prime is 0 or undefined. And you can see we're getting ready to try and figure out where mins and maxes can occur by talking about critical points. Critical points are places where f prime is 0 or undefined. We're going to use the words critical point a lot the rest of this year. There's also stationary point. And while our textbook authors might really like stationary point, yeah, I'm sorry, I know what it is, and I don't use it. F prime equals 0. A stationary point is a place where f prime is equal to 0. And a critical point is a place where f prime is 0 or undefined. So a stationary point is a subset of critical points. It's a point where not only could we be looking at derivative equal to 0 or undefined, but now we're refining it even narrower and saying, well, we're only interested in places where f prime is 0. Yeah, I don't have a lot of need for that, and I certainly haven't seen this in the last 15 years show up as a thing on the AP exam. So feel free to know stationary point, but I probably wouldn't bother. Most of the time we're talking about critical points. Oh my god, did you find the critical points over there? Okay. Next, let's talk about mins and maxes. We have this easy case. A, B, C, D. And we can say here casually, I see a max at B, I see a min at A. Remember, I have a minimum here because all the values in this neighborhood are bigger, higher y values than the y value at that point. Happens here too. I got a lot of different y values here. The lowest of them, the smallest of those y values happens here, and therefore this is a min. I got a max over here, I got a max over here. And the only way I can tell which of these is the absolute max we're saying right now is to plug both of them into the original function and find out what y values you get and compare those y values. Okay, and likewise here, if I want to know which is the absolute min, I've got two to choose from. I'm going to have to plug both of these x values into the original function, compare the y values, and that'll be fine. What about in a situation like this, though? How do we understand this? Here's a graph of piecewise f of x. What do you think? Mins, maxes, can you say anything about them? I can. There's no min and no max. These points aren't included. If these points were included, then I would have a maximum there. But that point is not included. And as a result, what's happening here is forever we are getting closer and closer and closer to a y value here. In fact, we know the limit exists over here, but the point doesn't exist. And because the point doesn't exist, we're just going to keep increasing and increasing and increasing and getting higher and higher and higher and higher and higher than the point before it. And because of that, we say no max. Okay? If I have something like this, I got two mins, I got a max. But if I take that out, I don't have a max. Okay? Here's a max. Here are two mins. Oh, no max anymore. Okay. So, we have some visual understanding, and I guess that's kind of what I want to say about this stuff is, to me, it makes a lot more sense in the context of a graph. If I have a graph of this function, and I find those places where f prime is 0 or undefined, and I check the endpoints, it's easy for me to see with my eyes whether that endpoint is a min or a max. And so I'm going to sort of depend on that kind of lame thing right now to get me through some stuff. Okay, let's just review again, because really I should give you a CFA just on this. Mins and maxes can occur on at endpoints of a bounded interval 2 where f prime is undefined, and 3 where f prime is 0. Now, I do want to warn you about this, and you might want to pull out that highlighter. Yes, the mins and maxes occur at all of these, but disproportionately, we will experience lots of situations where there are no endpoints, where the derivative is not undefined anymore. And as a result, we'll be looking at places where f prime is equal to 0 a lot more than these other two. And so maybe we should use stationary point. But no, because when we do that, we start forgetting about these. And that's what happens to a lot of kids in the United States. They completely forget that this isn't the only place we look for mins and maxes. We look for mins and maxes at endpoints. We look for mins and maxes where the derivative is undefined, as well as where f prime equals 0. Please don't forget these. I certainly will when I write your tests. Okay, so now that we've got this in mind, let's try some problems, okay? How about f of x equals 1 over x plus ln of x on 1/2 to 4. And I'd like to know about finding mins and maxes. Well, I'm a little scared the first time I see this because I think mins and maxes, well, wait a minute, that thing's got a vertical asymptote and so does that. But both of these have a vertical asymptote at x equals 0, and we're not going near x equals 0. There's an infinite number of points between r x equals 1/2 and x equals 0. Now, I'm not going to try and graph this by hand. I will, though, find f prime. So the derivative of 1 over x is negative 1 over x squared, and the derivative of ln of x is 1 over x. And if I tidy this up and make a common denominator, I would have negative 1 plus x over x squared as my f prime. Okay, so how do I find when f prime equals 0? Well, the top is f prime equals 0, and the bottom can be f prime undefined. When I set this equal to 0, when I set this x squared equals 0, I get that f prime is undefined at 0. And that makes sense to me because the original function had vertical asymptotes at those places. But look, f prime is equal to 0 when x equals 1. So I might have a min or a max there. I also have endpoints of a bounded interval. Don't forget, mins and maxes can live there too. So I've got 3 candidates right now for mins and maxes. I know because this function is continuous on this interval that I'm guaranteed min and max. So here's what we're going to do. We're going to go back to f. We're going to find f of 1/2. We're going to find f of 1. We're going to find f of 4. I plug a 1 in half there. I get a 2 plus ln of 2. If I plug a 1 in here, I get 1. ln of 1, remember, is 0. And so that's 1 plus 0, or 1. And if I plug in a 4, I have 1/4 plus ln of 4. Well, yeah, so I feel sort of frustrated. I feel sort of frustrated here because I am going to have to pick up a calculator to figure out which of these is the min or max. I guess I could think about my ln graph. So there's 1, 0, and here's E1, and 4 is bigger than E. So I know the y value here is bigger than 1. This is bigger than 1 plus 1/4. So I know that f of 4 is greater than f of 1. And what about f of 2? Well, I have no idea how these compare. Oh, wait, says Nathan. Couldn't you write that as 2 squared and then bring this down? Yes, you could, Nathan. 2 plus. So, do you have a sense, though, of which is bigger? No, me neither. But what can I say about ln of 2? Well, ln of 2 is here. That's a little less than 1, but I'm adding 2 to it, so I'm definitely going to be bigger than 1. So I also know that f of 1/2 is greater than f of 1. Doesn't this feel horrible? I mean, we live in the age of the calculator. Take out the damn calculator and figure out which one. But here's the thing. If I'm taking out the calculator, why don't I just look at the damn graph and see where my max and min is? So, yeah, sorry. I rant a little bit. Okay. So, yeah, I promise it'll get better. It really will. How about this one? Y equals 2 sine of 2x, and we're looking at 0 to pi. Tell me about the mins and maxes here. Well, because we're excellent graphers, we know there's pi over 2, pi over 4, 2 pi over 4, and we've got a sine graph. And we have a max at x equals pi over 4, a min at x equals 3 pi over 4. Is that it? Why, no. I've just missed half the mins and maxes. Because even though I talked about the places where f prime was equal to 0, what about the endpoints? This is a minimum. It's the lowest point in its neighborhood, whereas x equals pi turns out to be the location of a maximum. So we've got a max at x equals pi and a min at x equals 0. Okay? It's easy to blow by those. These look like mountains and valleys. Yeah, I gotcha. But you've got to keep remembering mins and maxes occur in 3 places. Endpoints, f prime 0 or f prime undefined. Okay? Oh, by the way, with that last one, remember we have to identify the critical points of x equals, here, in fact, let's go back and do it that way. Okay, so we said that f was 2 sine 2x. Okay? So what's f prime? 2 cosine 2x times 2, or 4 cosine 2x. So when I think about this graph on 0 to pi, what's it look like? Well, it's pi over 2, pi over 4, 3 pi over 4, and start pi, come to 0, down, and back up again. So this is my f prime graph. And what I see on this f prime graph, look, no, these are not the places I want to focus on. We're talking about the mins and maxes on f, not the mins and maxes on f prime. That comes later. What we're concerned about, remember, mins and maxes can occur at endpoints where f prime is undefined and where f prime is 0. Well, look, this is an f prime graph. F prime is equal to 0 at these places. These are my critical points. So it might be worth my time to say, I know that f prime equals pi over 4 is equal to 0. Therefore, on f at pi over 4, I'm going to have a min or a max, maybe. And I know f prime of 3 pi over 4 turned out to be 0. And so maybe on f at 3 pi over 4, I have a min or a max. So I'm going to take this pi over 4, I'm going to plug it into, see, it's f. I'm going to plug into f. So 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. 1 times 2 is 2. And 3 pi over 4 times 2 is 3 pi over 2. The sine of 3 pi over 2 is negative 1. Negative 1 times 2 is negative 2. And what I can say is, this one's lower than that one, and therefore that one's a min. Don't forget, though, we also need to consider f of 0 and f of pi. Well, if I plug a 0 in here to f, I get 0. And if I plug a pi in here for f, into f at, and plug a pi in there, I also end up with 0. Do I have any sense as to whether this is a min or a max? None whatsoever. I don't. Don't know. You know, the only way I have right now, even though I've plugged these in and I was able to compare these, is to say, well, what's the graph look like? Soon, very, very soon, but not in this video, we will have a way to figure this out. Okay? So I guess what I'm really saying is get through 5.1 quickly. Okay? How about f equals the ln of x plus 1. Okay? And I'm interested to know about mins and maxes. Now, I know this function is the ln graph shifted left 1, so I know there's a vertical asymptote over here at negative 1. And I've got my graph. And, you know, when I think about this graphically, yeah, I don't have any maxes or mins because this goes down forever and this goes up forever. So that's a little frustrating. So let's introduce on 0 to 3. Okay? All right. So on 0 to 3, we can say here's 0 and here's 3. What happens with f prime? Well, we know how to take derivatives. Derivative of ln of stuff is 1 over stuff times the derivative of stuff. So tell me about this. Well, here I've got an f prime, and 1 over x plus 1 equals 0. Does f prime equal to 0? Well, let's see what happens. These cancel. I get 1. 0 times stuff is 0. 1 equals 0. So what I learned from this is that f prime is never equal to 0 on 0 to 3. And I see that here. There are no slopes here that are a slope of 0. All of these slopes are positive. Okay. Where's the other place we might find? Where's the other place we might find mins and maxes? Derivative undefined. Okay, here's my derivative. My derivative is undefined when that denominator equals 0. F prime undefined when denominator equals 0. And that happens at x equals -1. And, because we've been through pre-cal and we remember how to graph, we say, duh, there's a vertical asymptote there. The function doesn't exist, so of course f prime isn't going to exist there. So right now, my critical points, complete bust. The only place where I find mins and maxes here turn out to be at the endpoints. And so if I check f of 0, I get the ln of 1, which is 0. And if I check f of 3, I get the ln of 4, and we know that that's greater than 0. Well, at least I'd like to think you're comfortable enough with the ln of graph to realize that this x value going into that function over here at 4 is higher than this y value of 0 here. Okay. So, yeah, there's just not a lot of, I feel like I just kind of want to stop the video. Let's try one or two more. How about f of x equals 1 over x on -1 to 1. All right, so, f prime equal to 0, f prime undefined. And so if I try f prime is -1 over x squared. And I want to know when f prime is 0. Well, the numerator is never 0. I mean, if I set this equal to 0, I get -1 equals 0. So f prime equal to 0? No, not on this function on that interval. How about f prime undefined? Oh, f prime could be undefined when this was equal to 0, like at x equals 0. At x equals 0, f prime is undefined. However, we all know that at x equals 0, we've got a vertical asymptote. So, of course, the derivative can't exist there. So where else do I look for mins and maxes? I look for mins and maxes at endpoints. So I've got f of -1, and I've got f of 1 to consider. Okay, so I plug my -1 in, I get -1, and I plug my 1 in, and I get 1. And I'm ready to say max and min. However, we've taken pre-cal. Here's 1. I'm sorry, -1. X equals -1. X equals +1. There's that vertical asymptote. Okay. Is this point the minimum? Remember, based on comparing these y values, we said this would be a minimum. But when we look at the graph, oh my goodness, it's a max. It's the highest point in its neighborhood. And over here, where we said there would be a max at 1, yeah, no, that's the lowest point in its neighborhood. It's all very unsatisfying to me. My ears are all pointy because of that. Again, you just have to bear with this a little bit longer. Let's see. How about this one? I'm not going to do that, but this one is good for us. Oh my goodness, this is a great test question. 4 minus x squared. All right, mins and maxes. Well, before I get to mins and maxes, I want to think for a minute. Domain. Can the domain of this be negative infinity to infinity? How would you know? Well, I agree. I can put any number I want in there. But here, what can't I have under a radical? I can't have a negative under an even index radical. So I'm going to find some critical points where 4 minus x squared equals 0, so x equals plus or minus 2. So what happens if I plug a 3 in there? 3 squared is 9, 4 minus 9, negative 5 squared is 9. Oh. So this graph, made up of a semicircle times this linear equation, this graph has a bounded interval. Hey, you know what? It was an implied boundary. There was no on negative 2 to 2 here. We were expected to know that these were endpoints. Ooh, chilling wind blows. Don't worry, there's a bunch of practice with this. Okay, so let's find y prime, because in addition to checking the endpoints of the bounded interval, I'm looking for where y prime equals 0 or where y prime is undefined. I'm also going to find my life is made easier if I use rational exponents like that. And now I have a product rule. So y prime is going to be 1 times 4 minus x squared to the 1 half plus x times 4 minus x squared. Ooh, take the derivative of the outside. Don't forget to subtract 1 times the derivative of the inside. A lot of people drop that because they're so busy thinking about the chain rule over here. All right, so what can we do? Well, we can factor out. I've been promising you this for a year. We can factor this GCF of 4 minus x squared to the smaller power out. What are we going to left with? 4 minus x squared over here, then our plus sign. Now here, I've got this negative 2x, I've got this 4, this 1 half. Let's multiply and turn that into minus 4x. And all of this is already coming. So that's what I've got, I think. Let me check. I've got that. Took the dirt. Where did the x go? I lost my x. 4x. Yeah, no, don't trust it. Starting it again. Okay, product rule. There we go. 1 times 4 minus x squared to the 1 half. Great. So we take the derivative of that times that stuff plus that. See, that's the x I'm looking for. Times the derivative of this, which will be 1 half 4 minus x squared to minus 1 half times the derivative of the inside, that minus 2x. Okay, so this 2 and this 2 can cancel, and an x times that negative is going to give me negative x squared. All right, so I'm pulling out the 4 minus x squared to the smaller power, and what's left over? A 4 minus x squared from in here, that plus sign, and now we've got an x times an x with a negative in front, so that's minus x squared. So here we've got 4 minus 2x squared times 4 minus x squared to the negative 1. There's our f prime. Now, an interesting, maybe even a nifty thing is simply by setting f prime equal to 0, here's my f prime. When I set f prime equal to 0, I'm finding the critical points. I'm finding where f prime equals 0, but I'm also finding when f prime is undefined. Why? Because look, if we flip that down, so our f prime becomes 4 minus 2x squared over the square root of 4 minus x squared. When this is equal to 0, gives me when f prime is undefined, and when this is equal to 0, I get when f prime equals 0. So setting all of this equal to 0, that's going to get me all that stuff. Now, 4 minus x squared to the negative 1/2 equals 0. You know, with rational exponents, I'm raising both sides to the negative 2 power. And over here, I get 4 minus x squared equals 0. I get 4 equals x squared, and I get x equals plus and minus 2. So I've got plus and minus 2. Now, what about setting this guy equal to 0? All right, well, let's see what happens there. So 0 equals 4 minus 2x squared, and then I get 2x squared equals 4, or x squared equals 2, or x equals, don't forget, when you take the square root of both sides, you've got to remember that plus and minus. So I've got negative root 2, I've got positive root 2. These are all places where f prime is undefined, or when f prime is 0. And so these are all candidates for me to test in my original function. Remember what the original f was? F was x square root of 4 minus x squared. All right, well, let's see what happens. I plug these values in. I plug in a negative 2. Negative 2 squared is 4. 4 minus 4 is 0. I get 0 times negative 2, which is 0. So f of negative 2 equals 0. How about f of negative root 2? If I plug negative root 2 in there and square, I have negative root 2 times negative root 2 is going to be positive 2. 4 minus 2 is 2. So I'm going to have negative root 2 times root 2, which is negative 2. And if I do f of root 2, okay, so root 2 times root 2 is 2. 4 minus 2 is 2. And so I've got root 2 times root 2, or 2. And then f of 2. Well, 2 squared is 4. 4 minus 4 is 0. And I get 0 again. Again, I don't feel like I have a really good sense of mins and maxes, except to say, that sure looks like a max to me. That sure looks like a min to me. But it's only when I think about this graphically do I have the sense that here, negative 2, I have a max. Here, positive 2, I have a min. Here, at square root of 2, I have a max, and that's consistent. And here, at negative square root of 2, I have a min, and that's consistent as well. But these, yeah, no, not yet, but it's coming. Luckily, we can think graphically tonight. Okay, I think I'm going to stop us there and see what assignment 59 holds.